This is the first of several tutorials dealing with transient analysis. A review of circuit theory follows. In general, when a circuit is excited by some external waveform, the total response is the natural response plus the forced response. The natural response is a function of the internal natural frequencies of the circuit. The forced response is a function of the external excitation and exhibits its form. Now, for a stable circuit, the natural response vanishes after a sufficiently long time, so we redefine the natural response as the transient response, and the forced response becomes the steady state response. So in casual usage, one discusses the transient plus the steady state, but in general, it's natural plus forced. Now, what Multisim defines as transient analysis is really more than just the transient part. Depending on the way the parameters are set up, one can actually see the total response, or you can set up your parameters in such a way that you see basically the steady state response. So we'll see that in this and later tutorials. In the DC steady state, that is when all transients are zero, capacitors act as ideal open circuits, and ideal inductors act as short circuits. Notice I put the adjective ideal in front of inductors because they tend to be less perfect than capacitors. All inductors contain some internal resistance, and that can be a factor in modeling a circuit. Capacitors are also imperfect, but they are much more perfect in general than inductors. Another thing to mention here is that in non-impulsive conditions, whenever an impulse function is not assumed in the input, the voltages on capacitors cannot change instantaneously, and the currents through inductors cannot change instantaneously. This means that an initially uncharged capacitor acts as a short circuit. Now, it's not really a short in the sense of conduction, but it acts as if it's a short in the sense that you can't create voltage across it instantaneously. You can have current flowing around the circuit external to the capacitor, and so it acts as if it's a short circuit. And likewise, currents through inductors can't change instantaneously, so if the inductor initially has no current in it, it will initially act as an open circuit before transients have vanished, or before transients have been generated. Okay, we have here, as I've done in previous tutorials, a simple circuit to illustrate the more involved aspects of multisim, circuits that can be readily analyzed by mathematical techniques. In this particular case, we have a first-order circuit consisting of a resistance and a capacitance. Now, the time constant associated with that is the product of R and C, 1 kiloohm, 1,000 ohms, and 1 microfarad, 10 to the minus 6 farads. The product is 10 to the minus 3 seconds, or 1 millisecond. And I have an external voltage of 100 volts applied to the circuit. Most of these parameters, some of the labels and so forth, were left in the same way that they came out of the bins. Node 1, node 2, this could be relabeled as input and output or whatever one desires. Ground node being 0. I left the V1, R1, and C1 as they came out, and the 1 and 2 as they were initially labeled. I did change the voltage here to 100 volts, and of course I changed the R into C to illustrate the phenomena. Now, if you go back to basic circuit theory and look at what would happen, the capacitor, if it's initially uncharged, would act as a short circuit, so the voltage across it cannot be established instantaneously, so it would start out with V2 being 0. However, as steady state conditions are reached, the capacitor becomes an open circuit, so the entire 100 volts here will appear across the output over here. So we would expect the circuit to behave as the following. The voltage on the capacitor will start at 0 and eventually approach 100 volts. the time constant is 1 millisecond. Now let's look at what's going to happen. First of all, let's look at the circuit here and make a guess. There's something here that has to be considered. This looks like it's been there. It's already set up. There's nothing to suggest a transient. We don't have a switch, and we have a DC voltage across it. Well, let's see what that gives us. I'm going to click here on the grapher, and I guess the curve is already, no, I'm sorry, this is a curve from a previous run, so let me get rid of that and show this situation, transient analysis. Okay, here is the window for transient analysis. First of all, the way it comes out is default. I'm going to go back to the default value that would come out when you first set up a circuit, is automatically determine initial conditions. That is the default. And down here, the default is generate time steps automatically. Let's discuss this one first. Automatically determine initial conditions assumes the circuit is in steady state unless there's something to tell it otherwise. Now back down to this area here, they generate time steps automatically as the easiest one to employ. However, it must be monitored to some extent because sometimes it doesn't always converge the way it should. Transient analysis takes a bit of judgment to deal with properly, but I'm going to leave it for this purpose. This is a simple circuit, and generate time steps automatically should probably be okay. So I'm going to leave it there for this particular case with a DC input. However, again, I'm going to leave the default here, automatically determine initial conditions. Let's check the output. It was already set to be of 2, the voltage at node 2 with respect to ground. Notice all these other variables, but I don't want to look at those right now. Okay, I'm going to hit simulate, and look what happens. I get a straight line. The reason is there was nothing in the setup that told it to run through the transient, even though the name of the operation is transient analysis. And I won't try to extrapolate. I could change the scale where you can see this or actually measure the value, but I think your imagination can see that it's going to be about 100 volts because that is the steady state voltage across the capacitor. The problem was that I did not force the circuit to go through the transient phase. By having a DC voltage and by going back to that particular option, let's look at that again, transient analysis. By assuming the automatically determine initial conditions, it put the circuit in steady state. So whenever you set automatically determine initial conditions, the circuit will automatically assume steady state conditions. What I want to do is go down here to set to 0. What that does, that set to 0 will set every voltage on capacitors to 0 and current through inductors. We don't have any inductors in this circuit, but if it had any, it would set 0 current through those inductors. 0 voltage on capacitors, 0 current on inductors. And let's go back and set the, I guess I didn't talk about this earlier, but I need to now. We want to go to 5 time constants, starting from 0. So it's 0 to 0.005. That's 5 times 10 to the minus 3, or 5 milliseconds. Notice this particular slot that you can only set seconds. So if you had to set a microsecond, I would put it in as 1 e to the minus 6. Some of the slots you can set in milli and micro and so forth, but not this one. Again, I'm going to leave it on generate time steps automatically, the easiest one to use, and hit simulate. Well, we see what we expect to get. The voltage starts at 0. It exponentially builds up toward a final value of 100 volts, and in 5 time constants, 5 milliseconds, which is a pretty good rule of thumb, it has reached essentially steady state. In 1 time constant, it reaches roughly about 2/3 its 1 minus e to the minus 1, I believe it is, if my memory serves me. It's about 0.637 times the final value. But it's, at any rate, in 5 time constants, it is settled for most, but not all practical purposes. So we have the exponential. Okay, let's get rid of that. Now, suppose we wanted to set something other than 0, that automatically set to 0, or whatever that option was of setting to 0. Suppose I wanted to set this at minus 50. Suppose that capacitor I wanted to start it at minus 50 volts. That is, plus down here and minus up here. Okay, let's click on the capacitor. And you notice something here that says initial conditions. That had been unchecked in the initial run. Now, of course, I won't go through this, but I could actually set it at 0, and it would give me the same effect as I had before. But this time, I'm going to set it at minus 50 and set that as OK. Now, this time, I'm going to go back to the transient analysis, 0 to 0.05. I don't want to set that to 0 because I've already put an initial condition on it. What you do is set it to user defined. User defined. Again, generate time steps automatically with user defined. Simulate. And the curve initially looks like it did before, but once you look at the scale, you'll see there's a difference here. It's now starting at minus 50. That's halfway between minus 25 and minus 75. Minus 50, but it's still charging toward plus 100 volts, as it has to be based on steady state. So now the voltage on the capacitor is minus 50 volts. It cannot change instantaneously. So it is starting at minus 50 and exponentially charging toward plus 100. Now, this represents a simple circuit. I'm going to use this circuit in at least one other tutorial dealing with a different kind of input. Well, actually, I think I have enough time to show one more input before I get any further. Let me go back and set this, get off the initial condition again, remove the initial condition, but show you one other situation here. And that is, I'm going to replace this 100 volt source by something that has been added, I believe, in recent versions of Multisim, and that's a step voltage. I don't think that appeared in some of the earlier versions. Anyway, we replaced it by a step voltage. Now, a step voltage is a DC voltage that starts at 0 and jumps up to 1 millisecond. Now, in this case, I want it to have the initial level of 0, a final level, let's say a 100 again, and a stop time, step time of 1 millisecond, output rise, fall time. Really, I want to make that smaller. I want a step time of 1 microsecond. And just go ahead and do an OK on that. And let's do a transient again. But this time, I'm going to go back as if it's set to 0, because the step function doesn't start until t equals 0, and hit simulate again. And once again, I get the step response. I personally am more have more experience using the DC and setting the output to 0, but this is a fairly new utility for Multisim and certainly worth investigating. That concludes this particular tutorial.